Computer cooling is a very critical and crucial part of designing a computer. Without it, it's impossible to run a computer because it handles the basic principles of thermodynamics and how the heat is dissipated from the computer. Computers generate a lot of heat by consuming power, and if that heat is not controlled, the parts inside can slow down, malfunction, or even burn out completely. For example, a running processor without cooling can easily reach temperatures above 100 degrees Celsius, which is hot enough to permanently damage it in just a few minutes. So, cooling isn't just an accessory, it's a survival requirement for any computer system. There are basically three types of cooling. They are passively cooled, air cooled, and liquid cooled.
Well, we learned why cooling is needed and what types there are. Here is a short description about them. A passively cooled system is one where there are no fans or other moving parts. It's done by measures of temperature or some other flow system, thus the heat is ejected. A good example is small devices like routers, Raspberry Pi boards, or some very thin laptops that rely only on heat sinks to spread out the heat without any noise. In an air-cooled system, there is always an active fan to push or pull air into the metal cooler to remove heat. Cold air takes heat from hot metal. This is the most common type used in almost every desktop and laptop because fans are very cheap, easy to replace, and reliable. The downside is noise and dust build up, but overall it's simple and effective. In liquid cooling, pumps and radiators are used to remove heat from the computer components. This type is usually found in high-end gaming PCs, servers, workstations where heat output is too much for normal fans to handle. The liquid carries heat away faster, but the system is more expensive and requires maintenance to avoid leaks or pump failures.
The new types of passive coolers are now found in many areas, where zero noise level and no movement of air is required for operations. For example, medical machines, satellites, and military devices often prefer passive cooling because any moving part could fail or create vibration. The new technologies involve thermosiphon. In the old heat pipe technology, the problem was that when too much heat occurred, the water inside the pipes would all turn into vapor and could not liquefy fast enough because it could not remove heat to the environment quickly enough. This caused what we call dry out or heat saturation. But the thermosiphon uses gravity to pull down the vapor and turn it back into liquid faster by improving heat efficiency and lowering the chances of heat saturation. This means we can cool much hotter components silently with better reliability, which is a huge advantage for panelless design like silent PCs or thin electronics.
Next, let's talk about the new air cooler, the 4-airjet cooler. This cooler uses air jets to blast air onto the cooler, and as it does that, the air gets heat saturated, thus removing more heat from the components. But the key shining point of this technology is that it does not require a rotating fan but relies on just a flat surface moving very fast to move air. This not only removes the bulky fan but also makes the design very thin. The airjet cooler is only about 2.8 mm in thickness, which provides a huge leap forward for thin and light machines like ultrabooks, tablets, and even VR headsets. To compare, a traditional laptop fan is usually 5 to 8 mm thick, So we can imagine how much slimmer devices can become with this new tech. And since there are no spinning blades, it also avoids dust clogging and reduces the mechanical failure risk that fans usually suffer from after a few years. Companies have already demonstrated prototypes where these air-jet coolers keep CPUs and GPUs cooler than traditional fan of the same size, which shows a promising future.
Finally, let's talk about lake-cooled servers. As we step into the new era of technology and AI, data centers use more power than ever, and this has become a big problem for conventional cooling systems. Servers in large data centers can consume the same amount of power as a small city. Keeping them cool with just air conditioning becomes very expensive and wasteful. Thus, plans of servers being built on the side of lakes are becoming a reality now. One such company is Equinix, which is experimenting with this idea. Their servers work a little like a nuclear power plant, where all the servers are essentially cooled by lake water. The servers are placed inside watertight cages, and chilled water and coolants are flowed through them. Heat exchangers are then used to dispel the heat into the lake in a controlled way. This method massively reduces electricity costs for cooling and also helps with sustainability, since natural water resources absorb heat more efficiently than just blowing air with giant fans. Some companies are even looking at underwater data centers, like Microsoft's Project Natick, where entire servers racks are placed underwater to use the ocean itself as a natural cooling system. These ideas might sound futuristic, but they are being tested right now, and they could change how we design big computing systems in the near future.